So the topic of the paper, the title is a little bit long, so I will skip reading the title actually. So what I'm going to do now actually is that I'm going to, how can I make this disappear? Oh, okay. So I'm going to spend the first part, of this talk just telling you a little bit about what we are doing in our lab. The lab is the Merlin lab in Milano, in Italy. And so I will spend the first part on this, and then I will go into more technical details about the part that is reflected in the title of this talk. So dual arm, teleoperation of dual arm with visual servoing. So in our lab, we are working mainly in industrial robotics, mission planning, control, collaborative robotics. Everything that is more or less related to industrial robotics is something that we try to address, and specifically in recent years, we have been working a lot on collaborative robotics. So just to frame, what I'm going to tell you within the scope of this workshop. So the very first part is about the full autonomy of the robots. I will show you something with the dual arm robotic assemblies. Then I will move to a form of shared autonomy, which is a human-robot collaboration, as Christian was actually saying a few minutes ago. This is a form, in a way, of teleoperation, of shared autonomy, when human and robot are interacting one close to the other. And there is another form of shared autonomy where you have the human that is actually remote, and this is telerobotics. So starting from full autonomy, I'm showing you this video where you see this dual arm robotic assemblies. You have the featureless assembly of arm devices. And then the nice thing in this experiment was that the robot was completely, without any vision and force sensor, and was able to do this in-hand operation by just using the mathematical model of the system in order to use a kind of admittance control to compensate for unavoidable misalignments. And then we turn to this first form of shared autonomy, which is human-robot interaction. And first of all, we focused on safety human-robot interaction with an eye, to industrial application. So what we did was actually this method to scale down the velocity of the robot in a way which is fully consistent with the ISO safety standard. So it is actually ready to be certified, of course, provided that the sensor that you use is safety rated. And we did so also with use of some prediction of space occupancy by the human, so-called sweat volumes that you can see in the corner, on the right-hand side of this video. And then we move to ergonomics. I know that today we have talked a lot about this, and this is an experiment that I actually described in a similar workshop as the one of today in Macau last year, where you had this robot that is interacting with a human, helping actually the human in this kind of operation. So actually the human is perceived by a 3D camera, and the robot is helping the human by offering this kind of bulky object in a configuration that is the most convenient from an ergonomic point of view for the human, and this also reduces the exposure of the human to musculoskeletal disorder. And we then moved to what we call intelligent collaborative robotics, where the collaboration or the interaction is not just physical, but it also has a kind of cognitive layer, where you have the human and the robot cooperating, and the robot actually understanding what the human is doing. And in this example that you may have seen in other presentation of our group. So the idea is that the robot is understanding what is the current action the human is doing, so classifying this action, and understanding, so the example is quite simple, whether the human is taking a box, the cover, in order to complete the operation. And all of this thanks to some cognitive vision that is used and is interfaced to the robot controller. You can push this idea a little bit further, and instead of just classifying the current action the robot is doing, you can also try to predict the next action the robot, the human will do by, again, using some inference. And the idea is that the robot is continually monitoring the behavior of the human, so trying to guess what will be the sequence of future action in order to be ready, as in this moment, to offer assistance whenever the human actually needs use of the so-called third hand. And so the robot is always synchronized with the human, and we kind of prove that from an empirical basis that this can actually save you kind of 30% in terms of productivity expressed as the cycle time of the overall assembly. Of course, in order to do so, you also need some techniques, some algorithms to understand what is the rate of advancement of a certain operation the human is doing. And we did this within a kind of mathematical framework, which is called dynamic time warping, which actually compares the current activity the human is doing with a kind of template activity. And there are ways, to estimate the percentage of advancement of a certain action, so as, to schedule the activities of the robot appropriately. And if you put this all together, you can do pretty nice things. Like controlling an overall collaborative production line. Here you have this example where you have actually 6 agents, the 2 arms of the robot, the single arm of the orange ABB IRB 140 robot, the 2 cards that are moving forward and backward, and of course the human that is another agent. And there is this kind of digital twin of this station that is in charge of acquiring all the information coming from vision sensor, understanding the situation, making some real-time analytics, making some what-if analysis, meaning that I kind of make forecast, what will be the consequence of some scheduling of action from on the robot side, and then to decide what is the actual best schedule that you need to assign to the artificial agents in order to maximize some optimization criteria. And you can see here there's a kind of a complicated example where the overall goal was to assemble a box with a USB pen with also some quality control check. And if you enrich this also with some more new ingredients, which is mixed reality, you can do this. In this video, you also see this device, on the top part of the picture, which is a cognitive vision system that is made by Smart Robots, which is a spin-off of a group, and that is in dialogue with the robot controller. And here the example is the assembly of a thermostatic valve. You can see that the robot is always observing what the human is doing, so now I understand that he has taken a piece from the lower tray. And thanks to the mixed reality device, the human is instructed on what is the operation. Of course, this is quite simple, but it's just, of course, a proof of concept. And the robot still observes. Now it understands that the human is picking another object from the upper tray. So it suggests to the human what to do next. You can see this, the human picks the complementary part, is again instructed by the mixed reality device of what is the correct assembly operation. It performs this, and the robot completes this part of the assembly. And this is an interesting part because here the robot is ready to substitute, replace the pallet, but it waits until the human, frees the part. This is the most advanced, example that we can have. And by the way, this is also made is a use case of the use of 5G technologies, because all these devices are connected in 5G, with 5G connection. And very recently, this is quite new, we also made some work on the psychological effect, of human-robot interaction. This has been recently published in the IEEE transaction of cognitive system and development. And the idea here is that we make this, this cooperative task and with volunteers with the two variants. In one case, it is the human that is the leader, so it decides what is the color, and the robot is the follower, while in the other case, the other way around. And we made experiments, and again, from an empirical basis, we can say that when the human takes the lead, he or she is subject to a lower psychological stress, but on the other hand, he or she is less productive. And this is the first step that in this kind of new branch of research that we are trying to explore on the psychological effect of human-robot interaction. So that's for the part, of the activities of our lab on the human-robot interaction, in terms of physical, cognitive, and also psychological interaction. But if we come back to the issue, of telerobotics, teleoperation, in this workshop, I do not have to make this kind of general introduction, autonomy versus shared autonomy. There is something that has been already mentioned several times here. And the telerobotics is a kind of old technology. It's been around since several decades, but is still quite, used in all the situations where, you cannot afford the full use of autonomy. And this is the case of medicine for minimally invasive surgeries, pharma and energy, where you need, to handle hazardous materials, space in orbit servicing, and exploration with the search and rescue in inaccessible environments. So these are all examples why telerobotics is still extremely useful today, and there's also practical application. And bilateral teleoperation is something that you have, of course, already talked about in this workshop, so I will not go into any detail about this. So I will present two works that we have made in the recent past. This is mainly the work of my former PhD student, Davide Nicolis, who is now working somewhere in the UK. So the first work was about identifying a virtual fixture to help, the work, of the operator in telerobotics, and with a kind of definition of virtual fixture that, is kind of independent of the definition of the controller. So the bottom line is that we do have hard virtual fixture that define forbidden regions for the teleoperation, but also soft virtual fixture that might be kind of guidance for the teleoperator. And the force feedback that is sent back to the human as a kinesthetic kind of feedback comes from the dual solution of the optimization problem. And things work like this, a little bit of mathematics, but not that much. So you have a quadratic optimization problem, which is related to kinematic coordination between the master and the slave. You do have some hard virtual fixture expressed as constraints. And what you actually are going to do with this quadratic programming problem is to minimize the tracking error given the hard virtual fixture, and then you propagate the solution to satisfy at best sort of this virtual fixture in order to, I mean, to also consider the second stage, I mean, objective of your application. And at the end, you obtain the slave control variables in terms of a joint acceleration that, of course, then are implemented by low-level joint controllers. And if you take the Crash-Tucker conditions for the first stage optimization problem, they can be written in terms of the Lagrange multipliers, in terms of the gradient of the optimization function and of the Jacobian, sorry, of the constraints. And you can give to this set of equation a nice kind of physical interpretation in the simplified situation of a single degree of freedom system, where the first one is the equation of the slave, that is just a mass that is subjected to the two kinds of forces. One comes from spring damper connection with the master device, and the other one comes directly from the virtual fixture, that is, it were a reactive force that is applied to the slave and is given by the Lagrange multipliers, the Jacobian of the constraint, and the Jacobian, the geometrical Jacobian of the robot itself, the slave robot itself, and is fed back to the operator as a force feedback. And the mechanism how this force is built is exactly this one. And also in the second stage, you can make something similar. And I have here an animation of an actual experiment, where in this animation you had actually a virtual fixture that was avoid any collision with that vertical bar, another virtual fixture that was avoid the collision of the end effector with the body, I mean, of the arm. Another one, if I'm not wrong, to avoid the collision with the table, and also to keep, I mean, that there is a right-hand camera in the, as you can see also in the left-hand side picture, in the, on the one hand, I mean, of the manipulator, and the idea is to keep the target always in the field of view of the camera, okay? And this is, I mean, how it works. So of course here the robot is teleoperated, and all the virtual fixture, I mean, guide the robot and actually constrain what the teleoperator can do. And here you just have some experimental results that basically tell you that field of view constraints are always respected, and actually sometimes they become active. We recently applied this kind of framework to a nice problem, which is teleoperation of a full robot that is carrying a glass or cup, whatever you want, with some liquid in order to avoid any spilling. This is by no means an easy task. So if you try to do this with just plain teleoperation without, I mean, just relying, I mean, on the position control, you most probably will pour out, I mean, the liquid from your container. It's not that easy, but you know, we don't go into any details here, just show you the video. But you can see that the robot is teleoperated, and it is possible to keep the I mean, the constraint, to respect the constraint of avoiding any spilling of the liquid from the glass door. I mean, it is teleoperated with all the uncertainties that are related to this, okay? And this is all model-based, so there is no actual feedback of the level, I mean, of the liquid, okay? And it was just made for validation purposes. The second kind of more advanced example is actually the one that gives the title, I mean, to this short talk. And the idea is that now you have this dual arm robot. This is actually this is the predecessor of the Yumi robot. It's called Frida, and we have the predecessor because, I mean, incorporated with ABB while they were developing the now known as a Yumi robot. And the idea is that you teleoperate the left arm of this robot with this moving Falcon haptic device. And there is a camera on the right, an in-hand camera on the right hand side arm. And the idea is that the user can only see the output of this camera, and so you want this camera to always give the best vision, I mean, the field of view, I mean, to the user, in order to help him, approach this goal, even if there are some objects in between that can produce some occlusion. And so the requirements of this application were to have an autonomous continuous camera positioning. The right arm of the robot was completely autonomous. You get kinematic coordination between master and slave teleoperated robot. So what you do with the master, you want to have it kind of replicated by the left arm of the robot. You want the teleoperated TCP and user-selected goal are visible at all times in the camera field of view. And you want that in case of occlusion, the camera autonomously reposition, so make some appropriate motion in order to always have the TCP of the teleoperated arm correctly in the scene. And overall, you want a natural and intuitive interaction of the experience for the human. A little bit of mathematics also here, not that much. We address this problem once again as an optimization problem, and in this form. Maybe what is interesting here is that when you want to relate the rate of change of the image features in the image plane, I mean, of the camera that is mounted on the right arm of the robot, you need to relate it to the joint velocity of the overall dual arm robot, so the 14 joint velocities. You can do this, of course, with some interaction matrix, but you need to be careful that, of course, what counts is the relative motion of the velocity of the end effector of where the camera is, and the velocity of the end effector that is still operated by the human. And by enforcing some mathematics, you can come up at the end with the image Jacobian that relates once again the joint velocities variable, sorry, with the rate of change of the image features. And it is nice, I mean, to see maybe how we have addressed the problem of occlusion in terms of a constraint that comes directly from what we have done in the completely different scenario, which is the human-robot interaction. And if you remember one of the first videos that I showed before, where we actually implemented the speed and separation monitoring principle. So the distance between, so the velocity of the robot has to be related to the distance between the human and the robot. And in pretty much similar way, you have here PT, which is the image feature of the target point. You have this object that can occlude your view, and you take one edge of this object, you take a generic point on this edge, you parameterize it with a natural coordinate, and you just impose that the distance between the generic point on this edge, of course in the image plane, and the image feature of your interest is always greater than the distance that can be covered with the relative velocity between the two image frame features in a given time frame. And this, I mean, can be, of course, elaborated, I mean, yields a kind of inequality in the natural coordinates that in turn, after some manipulation, entails at the end of the day some linear inequality constraints in the joint velocities, both the arm with the camera and both the teleoperated arm. And since our inputs are in terms of acceleration, joint acceleration, you can transform these constraints from the velocity domain to the acceleration domain with some tricks, I mean, that are used, I mean, in this situation. Also, we actually enforced a robust version of this occlusion avoidance constraint. I'm not going into details, so maybe just a short animation before going to the final video. Here you have an animation of situation where on the left-hand side you have a nominal formulation of the constraint, while on the right-hand side you have a robust formulation of the constraint that accounts for possible noise, in your vision system. And you will see in a moment that when you want to put the TCP feature on top of the goal one, in the left-hand side you will have occlusion. This is just the setup part, and here comes the approach part. Yes, and here it is. You have occlusion in one. Sorry, you have occlusion in the nominal case, and you do not have occlusion in the robust case. And finally, in order once again to give the best experience to the user, just placing a enforcing a constraint on occlusion avoidance is not enough. We resorted to this state machine that actually switches between some states. One is so-called the setup state, where you just set up the scene, and you will see in the video. This is the approach state, where you actually want to approach with your end effector the goal object, and the camera tries to give the best view, of both the goal and the end effectors. Also, the teleoperated end effector is, the motion is kind of constrained to achieve this goal. And in the conclusion state, once you have a clear view of the goal, you can release some constraints, and you can approach the final goal in a more easy way. And finally, you have also the occlusion state, where you have to reorient the camera to avoid the occlusion. And that's the final video where all these things are shown. Okay, this is the setup. On the left-hand side, you will see the scene from an external point of view, while on the right-hand side, you will see the actual output of the camera, so what the user is supposed to see. The idea is that the teleoperated end effector needs to go to orange goal. Here, okay, here you have a kind of occlusion, but you see here the reorientation of the camera that avoids this occlusion, and then you can safely perform the approach phase, and finally the conclusion phase, where the human can operate the arm more freely. This is the similar situation with the just change in the setup. So the occluding object is in different configuration, but once again the occlusion is detected, and then the constraint is activated. You can see a reorientation of both the camera and the teleoperated arm in order to once again give to the user the best point of view, and the task can be completed. And the very last part of this video is where you have the same situation, but in a kind of a dynamic, this was supposed to complete this, a kind of dynamic situation where the possibly occluding object is moved. Here you can see it is moved. So while the experiment has already started, so once again the occlusion is detected, so the camera reorients, and also at the end you will see that the user will move also the goal in order to also make the things a little bit more difficult. But once again, this is the system is robust, against this perturbation. And this is what I wanted to say you today. Thanks for your kind attention, and I'm ready to take your question, of course.
Thank you, Paolo, for the very nice presentation. We have a question. Have you ever experienced convergence problem of the optimization problem, especially when considering the occlusion constraints?
Actually, this is a question that should be made to my students. So actually, I did not perform myself the experiments, of course, But for what I mean, I can say the convergence problem were not that, I mean, a specific issue, I mean, of this approach. But I can't, so let's put it this way, I can't remember students crying for the convergence problem, let's put it this way.
Okay, thanks a lot, Paolo, for the nice presentation. It was a pleasure to have you as a speaker here.
Okay, thank you.